Hello, welcome. We're going to talk about buffers today. A little down to making that mistake. I still have no idea where those numbers came from. It's the disadvantage of doing these videos ahead of time, a day or two ahead of time. Looking back on my work, no idea where those numbers came from. But yeah, I totally screwed that up. I'll try to prevent that from happening again, but I'll probably make a mistake in just a minute. So it is what it is. Buffers and what they are. All right, it'll be fun times today. All right, buffers, what are they? They resist changes in pH, and what you're going to do to make a buffer is you're going to take a weak acid or a weak base, and then you're going to combine that with the salt of the acid or the salt of the base. So if you have a weak acid, you would combine it with the salt of the acid. If you have a weak base, you would combine it with the salt of the base. And I'll pull up the whiteboard here in a minute. You can see what I'm talking about. The best buffer, the buffer that's going to resist the pH, change in pH the best, will be a buffer that has the same concentration of the acid and the salt. When those concentrations are equal, that will be the best buffer. And you'll have the pH equal in the pKa. And we'll get to that in a minute. And with that being said, this is all fancy. Let me pull up the whiteboard and we'll look more in depth at buffers. All right, so I got the whiteboard up here. And my equation, this is hydrofluoric acid and the dissociation of hydrofluoric acid. Don't worry about this yet. We'll get to it, hopefully. So to make a buffer out of this is a weak acid. I would just add the salt of the acid, for instance, sodium fluoride, so NaF. When I put that into water, it's an ionic compound, so it's going to form Na plus and F minus. All right, so I've overloaded it with the conjugate base here, the acid. Anyhow, let's take a look at what will happen. If I add a strong acid to this system, all right, if I have hydrochloric acid, what I'm doing, if you remember with the strong acids and bases, 100% dissociation, I'm really increasing H+. Right, and I have an equilibrium system here, and with Le Chatelier's principle, as I increase my H+, it's going to shift back to just HF. So for every H+, I've got an overabundance of F- in there. It's going to take an F- and form HF, and it's not going to change the concentration of H+ to the point where it's going to drop the pH significantly. All right, so again, this is just an equilibrium, kind of Le Chatelier's principle thing going on here. So the H+ is not going to increase with that because it's going to be taken out, and the equilibrium is going to shift back to the reactants. All right, increase the product, shift to the reactants. All right, now if I have a base, and it's sodium hydroxide, let's go that one. Again, 100% dissociation. The Na plus is going to be the spectator ion. The OH minus. All right, where the acid is taking the F minus, or is combining with the F minus and going out. What's going to happen when I add base? All right, this hydroxide concentration is going up, but you'll notice H plus is there. So what's going to happen is H plus is going to combine with OH minus. It's going to form water. Right, and as I take this out of the equation as it goes down, right, this is a product that's going down, I'm going to shift my equilibrium to the products. So even though I'm losing H plus because of the OH minus here, in fact, the balance will be maintained pretty well, pretty reasonably for a time. And then the H plus, because it's going to form the H plus back again because the OH minus is taken out, but it's equilibrium. So the equilibrium is going to be maintained at that point. So again, that's a good review of Le Chatelier's principle and how buffers work. All right, just to recap, H plus, if I add an acid, it's going to increase my product, which is going to shift it back to the reactant. If I add OH minus, that's going to take H plus out of the solution, forming water. It's going to decrease the product, which means that my equation is going to shift back to the products. All right, so let's talk about how we can, let's get rid of this for now. Let's talk about how some problems we can do, calculating buffers and capacity and whatnot. So before I continue to go down to the problems, this system will be maintained until if I'm adding an acid, right, the system will be maintained until I run out of F minus. Once F minus is out, then I've got nothing to take out the H plus, and the pH will then skyrocket, or actually it'll go down. And if I have a base, right, it's going to be maintained until I run out of H plus. At that point, when I add more hydroxide, there's going to be nothing to combine with, because hydroxide and the pH will go up very rapidly. The other thing to consider is at equilibrium, or when I have taken out all of my H plus, and I've used up enough base, exact amount of base to take up all my HF to become H plus here. What I'm left with is F minus. So even though I have added the equal amount of base and acid to neutralize the solution, so to speak, the pH actually will be not at 7. It'll be above 7 because I have this conjugate base. Since there's a conjugate base here, the pH of the solution will be a little bit basic. Not hugely basic, but it'll be a little bit basic. So keep that in mind. Okay, let's look at a problem. All right, so we have a problem. I was tired of hydrofluoric acid, so I'm changing it to lactic acid. What is the pH of a buffer that is 0.12 molar in lactic acid and 0.1 molar in sodium lactate? Ka of lactic acid is 1.4 times 10 to the minus fourth. And here I have the equation, which this galaxy pen's driving me nuts. It's bleeding like crazy. It's hard to see, but again, the same concept. We have H plus and C3H5O8 minus, and this is my salt. So my salt here, and this sodium part will be my spectator ion. This will be the anion, the negative part. So if I do this like we've been doing it with the ice chart, oh my gosh, I don't know what my problem is today. It's just killing me. That's an I. I'm starting to get angry here. But in my ice chart. All right, first part easy. I've got 0.12 molar of the acid. H plus is going to be 0. And here's the wrinkle. Here's the new twist. I've added sodium lactate. All right, what is sodium lactate providing but C3H5O8? And I have 0.1 molar. So it's going to be 0.1 molar of that to start with. And my change will be the same. I'm going to lose X amount of that. It's going to dissociate. I'll gain X amount, and I'll gain X amount of the anion. So at equilibrium, I got 0.12 minus X. I got X, and I got 0.1 plus X. All right, now I can throw this into the equation. I end up with 1.4 times 10 to the minus 4 equals X times 0.1 plus X. Again, this pen is driving me nuts. Over 0.12 minus X. And it's easy. Just solve for X. That's a plus there. No problem, right? Distribute that, you get 0.1x plus x squared over 0.12 minus x. It's actually going to be kind of messy to do it that way. So luckily for us, we have what's called the Henderson-Hasselbalch equation, which is the pH of a buffer will equal to pKa plus the log of the concentration of the base over or divided by the concentration of the acid. So to get the pH, you get the pKa, which remember what does lowercase p mean? It is the negative log of that Ka. So I'm going to take the negative log of 1.4 times 10 to the minus 4, and I end up with 3.85. And I'm going to add that to the log of this definition of this division problem, where my base, remember the anion, was the sodium lactate, and that is 0.1 molar. So take 0.1 molar. And I'm going to divide that by the concentration of my acid, which is 0.12 molar. This is so much easier, right? And you do 0.1 divided by 0.12, and that gives you 0.83. You take the log of that. It is minus 0.079. So no 3.85 minus 0.079. That's right, it's a minus minus, and it's being a plus. So it's minus 0.79. Oh, no, it's plus. Never mind. Oop. It's just one of those days. And you end up with a pH of 3.77. All right, to recap, all right, with the buffer system, you can do it. You can go ahead and solve this way, and it's going to take you a little bit longer. And maybe those fancy graphing calculators you guys have will be easy. But if you use this equation here, pH equals pKa plus the log of the base over the acid, you end up with the pH. Right, so the pKa, negative log of the Ka, add to that the base divided by the acid, and take the log, and that's going to end up with your pH. Now, a couple notes. Remember, I said the best buffers are when we have equal amount of the salt of the acid and the acid. And what happens here is you have the same concentration divided by the same, right? This is 1. The log of 1 is 0, and what you end up with is the pH equaling the pKa. So if you have a question about a buffer and the best buffer, the pH for a buffer, that buffer you want it to equal the pKa. So if you take the negative log of the Ka, that is your ideal pH for the buffer. This stuff works for bases as well. You just have to change the notation around a little bit, and you end up flipping this, but it works the same for bases. And I'm out of time here, and hopefully it makes sense. I mean, really, it's just deciphering this information and putting it right here. This equation, this awesome equation, is what you need to use to get it right. All right, I've spent enough time here. Good luck, and again, reach out to me with questions. If there's a particular question, or I may make a mistake again. Maybe I made a ton of mistakes here. Probably. All right. See you.